Many Americans grow up watching the classic movie Mary Poppins and are fascinated by her preferred method of transportation, flying in from the sky on an umbrella. The Red Team, like other Poppins fans, are curious if umbrella flight is actually possible. Thus, we propose our final myth. Can a person like Mary Poppins safely fly in from the sky by using only a rain umbrella? Introducing the Red Team. Evan Johnson, Cameraman 1. Nate Schrader, Recorder. Andrew Bretz, Cameraman 2. And Paul Hudak, Experimenter and Live Tester. Similar to the ping pong ball myth, Myth 3, our Mary Poppins myth can be answered using the concept of drag force. When an object like Mary Poppins falls through a fluid, the object pushes against the fluid. Thus, as Mary falls downward, she contacts air, which pulls her upward, slowing down her velocity. The pulling is the drag force. There are two equations for drag force. Fd equals bv and Fd equals bv squared, where b is a simple way to describe the falling object's surface area and v is the object's velocity. We know the drag force is equal to the gravitational force, mg. Thus, we get one of two models for drag force. Fd equals bv equals mg, or Fd equals bv squared equals mg. Solving for velocity, we get v equals mg divided by b, or v equals mg divided by b to the half power. Since we divide by b, if we make the surface area b bigger, then the velocity should go down. Thus, because an umbrella's surface area is bigger than a human's, the falling velocity should decrease, and possibly decrease enough for Miss Poppins to survive a free fall. For our preliminary experiments, we want to verify which drag force model applies to our myth, the V model or the V squared model. To do this, we can hold surface area constant and change the falling object's mass. If velocity doubles when we double the mass, then we have a linear relationship with a straight graph and use the V model. If velocity doubles when we quadruple the mass, we have a nonlinear relationship with a curved graph and use the V square model. We then proceed to set up our experiment. Keeping surface area constant, we use small cocktail umbrellas and attach 2 gram, 5 gram, 10 gram, 20 gram, and 50 gram weights to their centers using tape and string. We drop the weighted umbrellas from the ceiling of our lab, but later drop the 50 gram weight from the home football bleachers nosebleed section high enough for the umbrellas to reach terminal velocity. Using a 2 meter scale in the video recording, we can later compute the falling velocity. Following our first test, we realized that we should also perform 2 more experiments and study 1. If the umbrellas even make a difference in falling velocity, and 2. If hanging the weight, like a body hanging from an umbrella, affects the falling velocity. The umbrella frequently flipped, and we believe hanging the weight will also reduce flipping and thus falling velocity. To see if umbrellas and hanging weights affect falling velocity, we drop the weights without umbrellas from the bleachers. Then, using string and tape again, we hang weights from the cocktail umbrellas and drop each weight. We then graphed all 3 preliminary test results. After our first test, we analyzed the video recordings using Logger Pro and calculate the weight's fallen velocities. Then, we graph the results and find that when the mass doubles, the velocity increases, but it does not quite double. Thus, relationship is non-linear, and that the average result graphs a curved line. So we will use the V-squared model for our full-scale experiment. Graphing all 3 experiments' falling velocity, we can see several things. First, we again see nonlinear relationship, further verifying our V-square model. Next, you should also notice the blue curve, which is our weight's only results, is above the other 2 curves. This shows that weights alone fell faster than weights with umbrellas, so umbrellas do indeed make a difference. For example, for a 50 gram weight, no umbrella fell fastest at 14.97 meters per second. The centered weights at 13.75 meters per second, and the hanging weight fell slowest at 11.56 meters per second. Lastly, the red curve is mainly below the green curve, which means the hanging weights fell faster than the centered weights. However, this may be incorrect because only the centered 50-gram weight was dropped from the bleachers, and it actually fell faster than the hanging weight. So in summary, we will use the V-square model and expect for an umbrella to decrease falling velocity. Before we move forward to our full-scale experiments, we must notice several things. Quickly, some numbers on falling and injury, or death. Through research, 6.1 meters poses clinical health risk. At 15 meters, people only have a 50% chance. The bleachers are about 12 meters high, so injury looks very plausible for Mary right now. Also, at deadly 15 meters, people fall at about 17 meters per second. And clinical health risk occur at about 11 meters per second. Our 50-gram weight fell at 11.6 meters per second. So, if Mary Poppins weighs 100 pounds, she weighs 73.51 kilograms, which is much larger than 50 grams. Because raising the mass increases falling velocity, we should expect Mary to fall much faster than the 50 grams 11.6 meters per second, putting her in the injury zone and maybe even the death zone. Additionally, some people have physically tested this myth on YouTube, and they seem to land with a lot of pain. To say the least, it's not looking good for Miss Poppins. Even though our projections indicate Mary Poppins cannot fly with an umbrella unharmed, we want to bust this myth with hard evidence. So again, we return to the bleachers for full-scale experiments. To avoid injury, we decide not to use Paul for a true test. We instead fill a book bag with 5, 10, and 25 kilogram weights and hang them from the umbrella using rope and, of course, duct tape. We then drop the book bag from the bleachers down into the grass. Keeping a scale on the video screen, we again can later compute the falling velocity on impact with Logger Pro. If the falling velocity is higher than 17 meters per second, our myth is busted. Andrew and Paul first dropped the weighted book bag at 3 weights without an umbrella for our base test. Then, we hang the bag from the umbrella and drop the different weights again. We notice to prevent the umbrella's top from inverting, we loosen the umbrella cover's tension. This prevents the air from collecting under the umbrella, and basically lets more air contact the umbrella cover as it falls instead of traveling around it, increasing drag force and decreasing falling velocity. Finally, we try to maximize surface area and attach two umbrellas to a wooden rod at arm's width and hang the book bag at the rod's center. We then drop the book bag containing 5, 10, and 25 kilograms. Using our recordings in Logger Pro, we again figure the falling velocity near impact and graph our results. Because the averages of the green and red lines are below the blue line, we can conclude that the umbrella does indeed increase the drag force and thus decreases the falling velocity. However, if we find 10 kilogram with one umbrella falls at 13.7 meters per second, and 25 kilograms with one umbrella falls near at least 17.3 meters per second, because Mary Poppins weighs roughly 45 kilograms, we expect her to fall even faster than 17.3 meters per second, which is in the death zone. In fact, even a child weighing 25 kilograms, or 55 pounds, can die from a 40-foot fall with an umbrella. So kids, even an umbrella won't save you from a really high jump. Don't do it! Mary Poppins falling much faster than 17.3 meters per second in the 17 meter per second death zone? Myth busted. Tune in next season as we use drag force to test our next myth. Can a person use Star Command wings to really fly like Buzz Lightyear?